My name is Volodymyr Khytskyi, and I'm one of the software engineers working at Intiv. And today I would like to talk a bit about WebAssembly and how you can start writing performant client-side web applications using Rust programming language. But before we get to agenda, I'd like to ask you, do any one of you have any experience with WebAssembly? Okay. What about Rust programming language? Cool. So I hope that a lot of you will learn throughout this presentation, and yeah, let's get started. So agenda for my presentation looks as following. First, I'm going to briefly describe what WebAssembly is, why it was created in the first place, and what problems it aims to solve. We're going to take a look how WebAssembly gets executed inside the browser. Afterwards, I would like to show you an example of one real-world application that already benefits from the technology. In the second part, I will finally switch to how you can start writing applications in Rust language and target WebAssembly. And I will finish by saying a couple of words about the technology and how it will shape the web. But first, what is WebAssembly? WebAssembly is basically another type of the code that can be executed by the browsers. Speaking a bit more technically, WebAssembly is a low-level assembly-like language that has compact binary format that was designed to be a compilation target for different languages, and current support is C, C++, and Rust. It was designed to work at near-native performances, also designed to work alongside of JavaScript, and it's abbreviated as WASM. But we all know that new technology, like WebAssembly, will not emerge in a web just out of nowhere, without a really good reason. And that reason is a demand for high performance. Being a dynamic language, JavaScript suits well to resolve most of the common problems that web has today. But there is a certain subset of cases where it's not that suitable, where there is a need for native level of performance. And here I'm speaking about 3D games, audio-video editing, virtual reality, and encryption. Another important thing that we should take into consideration is that functionality-wise, client-side applications are constantly growing. And right now we are in a situation that for a browser's virtual machine to download the deliverable, compile it, and interpret, it all actually takes a lot of time and takes a noticeable amount of time for the end users. Therefore, compared to that, WebAssembly was introduced, and the primary goal of WebAssembly is to make it easier for machines to read the binary instructions that are within the deliverable. So, speaking differently, WebAssembly binary format is designed firstly to be read by machines rather than humans. Another cool feature that WebAssembly provides is a streaming compilation. So the deliverable arrives to the client in a chunks of data. And streaming compilation is a feature that allows a compiler to actually compile the chunk of code at the moment it arrives to the client. So by the end of the download, the whole WASM module is ready to be executed up until that point. The second greatest feature of the WebAssembly is an amazing portability. Because WebAssembly was designed to be a compilation target for different languages, it means that you can actually compile the libraries and apps that were not meant to be run in a browser to the web. Speaking specifically about C and C++, since those languages are supported in almost every platform, including the mobile operating systems, But now it makes it possible to have single shared code base that can be executed and compiled to the desktop applications, to mobile applications, and to the web applications. Alright, now let's learn a bit how WebAssembly actually runs in your browser. Before that, we need to speak a bit about the web platform in general. Web platform in general can be divided in two parts. One is actually the virtual machine that runs client's code. The second part is web APIs that allow the web application code to interact with the browser itself and the device on which the browser is installed. And here I'm speaking about DOM, WebGL, some audio APIs, and so on. So when WebAssembly was shipped to the browsers, virtual machine got an ability to load two types of code. Regular JavaScript that we all know and love, and was WebAssembly bytecode. WebAssembly was not designed to replace JavaScript, and currently only JavaScript has access to those web APIs that I was speaking about a bit previously. Therefore, there was a need to make it possible for two types of code to communicate between each other. And that's why WebAssembly JavaScript API was introduced. JavaScript is fully responsible for loading WASM modules, to import its exports, and also to provide web API functionality to it. I'll explain these buzzwords a bit later in more detail. Let's actually take a look at the key concepts that are mapped directly to the already mentioned WebAssembly JavaScript API. And we need to keep in mind about four logical things that are present there. So first is the module, which is basically a compiled WebAssembly unit down to the machine instructions that can be directly executed on the CPU level, and that module is stateless. In order for it to work with the memory, a logical memory is coming in place, which is a linear array of bytes to which a module can perform I/O operations. Table is somewhat similar to memory, but it just contains the references, for example, to functions. This division was made for some security reasons, which I'm honestly speaking not aware. And the instance is a module paired with memory and a table. So at any point of time when we actually are requiring the WASM module, all these steps are happening behind the scene, and we are operating on instances directly. Okay, but for now, enough for the boring tech stuff, and I would like to show you one application that, there are many applications that benefit from WebAssembly, like SketchUp for 3D modeling, Google Earth that we all know, and Soundation that is designed for music creators. In my opinion, one application outstands all of them, maybe even together, and that is Autodesk AutoCAD. AutoCAD is a computer-aided designing and drafting software, and that is used by millions of engineers and architects nowadays. It is designed to create the world around us, and within this application you might even try to design something like this building. The development journey started at late 70s, and the first release happened in 1982. So this is a pretty old application. Over the course of the development, the codebase grew to an astonishing 15 million lines of code. And
but what's the code is in what language?
C++. Yes. Back then, well, there were no.
They never had idea to rewrite.
50 million lines of code. I don't think so.
But you mentioned that 50 million lines of code. It's today, yes. It's today after 46 years of the app.
Yes, I guess they started with Lisp.
I don't know the history that good. Well, it's up to the company. I'm not the person who can answer that question. The company made several attempts in the past to bring the application to the web, and there were released 2 products in the past. The first one was in 2010, and it was a Flash-based basic editor. Over time, they've transitioned to the JavaScript and HTML5. And of course, over the time, they were providing some additional functionality. But in general, this approach was not scalable enough because, again, of such tremendously big amount of lines of code that they have today. So, when WebAssembly was introduced, the development team saw another opportunity of trying to port their C++ code to the web. And after around 3 years of development, major milestones were reached one after another, and in 2018 they were finally able to release the web version of the application that is functioning and feels like the real desktop application. It was very warmly welcomed by the community, and in general for the development team it was a big success. Briefly about how they were porting the stuff. Well, nothing fancy. Again, at the very bottom, the C++ code that they were developing over the time, they managed to compile it to WebAssembly using the binarian toolchain. And the only new things that they needed to add is UI interactions. And that was done using modern technologies like React and TypeScript. And communication between JavaScript and WebAssembly is done via the API, via the messaging API that I mentioned previously. How can we actually start using WebAssembly? As I mentioned, my language of choice is a Rust programming language. And to answer your why question, here is the list of its features that I believe makes it a great one. So first, Rust is a system programming language. It is memory safe, though it provides low-level memory operations. There's such operations that you most likely will see again in C and C++. It supports both programming paradigms, functional and imperative. It doesn't have automated garbage collection. It draws an inspiration from many different languages, among which are Scala, C#, and Haskell. And according to the last survey done by Stack Overflow, it is one of the most loved languages. So this is the first library that we'll be using mostly often. Remember I was speaking about the messaging API between the JavaScript and WebAssembly. So it's quite low level, as it allows to operate only using numbers. Therefore, such a project was developed that is called Wasm Bindgen, and the aim of this project is to provide high-level abstraction over those communications, so that it will simplify our lives and provide an ability to use strings, classes, functions, everything that we would normally use, to communicate between the two code types. We are now able to take a look how to write the simplest application. Rust code looks like this. If you do not know Rust, it's okay. I believe after my line-by-line explanation, you will grasp the idea what is going on here. So the first thing is that we are importing our WASM binding module, and also we are importing all the exports from the prelude subpackage to the root namespace. It's just for convenience, so we don't need to write the whole path to some of the dependencies that we'll be using. Second thing is quite fundamental. So first line hashtag WASM binding is actually something that is in Rust called attribute. Basically, it will do the magic of importing the alert function from the window object inside of the WebAssembly. And it should be wrapped inside extern keyword so that the name of the function will not be mangled, and it will be easy. It will be properly referenced after this Rust code will be compiled. And finally, we are defining a simple greet function that makes use of alert, provides to it a preformatted string, and we're using pub keyword to export it to the JavaScript world, let's say. Okay, and JavaScript looks simply like this, just 2 lines of code. We are importing our WASM module as in a way that we would import normal JavaScript, and once promise is resolved, we can actually execute the greet function. Okay, last thing that is left for us to do here is to compile our Rust code into WebAssembly. And it is done with these two commands. First one, it's Cargo, which is a package manager for Rust programming language. And what it will do, it will actually, using the compilation target that is specified there, and using nightly toolchain, it will actually produce hello world.wasm file. Afterwards, we again need to use WASM binding, but this time a CLI tool that will also generate for the already created file glue that we will actually ship as a package to the JavaScript. So the result of the execution of WASM binding is 3 files. The first one is the raw WASM file that was generated from the first command, but it will be just like copied into the same location where the next 2 files are located. Second file is a definition file, so if you would like to import your WASM module into TypeScript project, you will have a definition file and you are ready to start using it. And of course, the JavaScript file that actually contains all the glue that allows two code types to cooperate. But in order to explore the possibilities of the WebAssembly, we need to transition to something a bit more advanced and complicated. Conway's Game of Life is a really nice example. So this is a cellular automation which doesn't require any user interaction during the game. You just seed the universe and you observe its evolution. And speaking of universe, it is a 2D orthogonal grid of cells. Each cell can be either alive or dead. And next generation is based on the interactions of each cell with its neighbors. There are 4 rules defined in this game, and the first one is stated like that. Under population, any live cell with fewer than 2 live neighbors dies. So in the example here you can see that we have three live cells, and the ones that are highlighted to the blue color are the ones that will change according to this rule. So in the next generation we'll just have only a single cell, because all those two have only a single neighbor, that is like in the middle. Rule number 2: any live cell with 2 or 3 live neighbors lives on to the next generation. Speaking about the same example, again, that is why the live cell in the middle stays alive, because it had 2 neighbors in the previous generation. Rule number 3: overpopulation. Any live cell with more than 3 live neighbors dies. And here you can see that we have something that can remind us a plus sign that gets transformed to the box, and the live cell in the middle dies. And why actually we get the box is because of the rule number 4, which is reproduction. Any dead cell with exactly 3 live neighbors becomes a live cell. So yeah, those again highlighted cells on a previous generation were dead, and all of them had 3 live neighbors. That's why we get the box. And so right now it makes no sense, but if we combine all of these things together, we can actually start observing kind of interesting things happening in the universe. And some of the examples can be like stable universes, where only rule number 2 gets applied, and it will not evolve any longer, no matter what generation we will take. Also, you get periodic universes. So on the right side, you have this weird thing that is called pulsar, and it gets back to the state it was like 3 steps before, I guess. And also you can get some weird stuff that kinda moves across the universe, and in this case it's called spaceship. How this can be coded, or how the demo application that I'm about to show you was coded, is that again we have obviously JavaScript part and WebAssembly part. I was speaking about memory, logical element, and this is visualized on the bottom of the slide, where we have a linear memory that can store either zeros or ones that represent dead or alive cell respectively. And since we know the dimensions of the universe, this can be easily represented as a grid. And the responsibility of the JavaScript is only to render the visual representation of this array to the user. All actual logic is happening inside WebAssembly. From the coding perspective, it looks like this. So again, business logic inside the Rust file. We have enum of name cell that represents the cell, universe, which contains the size of it and the state of each cell. And also there is this method called tick that calculates and generates next generation based on the current state of the grid. Again, on the right side you can see how we are importing WebAssembly into the JavaScript. First line is we are importing our glue, the JavaScript file that was created previously by was and binding. And also we are importing raw memory on which WebAssembly is operating with live_bg file. And we get the pointer to the location of the universe, and we represent it as a typed array, and later we have somewhere defined two drawing methods. Okay, so time for a demo. Yay! So here you can see some universe that was seeded with some weird data, and we can see how it transforms over time. On the very top you can see that I've created some small control panel, and let's take a look how it will emerge if we increase the FPS cap. So you can see that some parts became like periodic universes. I can see all those frames. So I'll lower it. Yeah, weird and funny stuff. So some parts of the universe are stable. Some are like you have a glider that going, and we also have some periodic universes. Yeah, looks weird. But
how do you define the status 0, the start of the game? Is it arbitrary or
you actually
random?
No, in my particular case, I specified that if, for example, if the cell index divided by some number equals to 0, then it is a live cell. If not, then it is a dead cell. So if I go back to the 1 frame per second, reload the page, and pause. So this is the initial seed that I fed to this universe. Why I believe this is a very good example? Because it actually illustrates how WebAssembly interacts with the raw memory and how this raw memory gets rendered to the user. So it's I believe nice representation of what is happening underneath of the application. All right. So when developing applications of such level, you would want to have some debugging tools under your hand when things go wrong. And it's a bit different from what is available in the JavaScript. So let's get familiar with those. First of all, well, since we are debugging, since we are compiling our code, a lot of stuff gets either obfuscated or it will be represented with a really low-level assembly-like instructions. And first thing that you will most likely to do is to enable the debug symbols, so that when you have a stack trace of the error, you'll actually see the real name of the functions instead of some unrelevant numeric value. So that will help a bit to debug the problem. Next thing is, very simple. Logging is also available. And using the same techniques I described previously, we could use WebSysCreate that will actually allow us, that will expose the console object to the WebAssembly, and we can write, we can log simple messages. Logging errors is a bit trickier, and the reason for that is because WebAssembly itself doesn't provide any error handling. Therefore, if you would not use any hooks like this one, you'll get an error like this that says runtime error unreachable. But luckily you have your debug symbols enabled, so you can at least track down where the error appeared. So in this case, it appeared in universe.new method. But with such hook, it will provide you extra information. It will show you what exact message an exception throws, and it will also hint you in what file, at what row, and at what column this error occurred. and using a debugger. Unfortunately, the situation is I would say poor, since there are no source maps like that are working out of the box available right now. And if you would like really check how WebAssembly operates, you will have to step over those machine instructions, those assembly instructions. Despite that, native source maps are on their way to be implemented in the near future, and there are some experimental approaches of how to do this, and those I've linked in the bottom of the slide. Time profiling. If you've decided to use WebAssembly, that most likely that you are trying to build something that should be highly performant, and therefore you should use your performance budget reasonably. And let's take a look of what techniques we could use. Probably you know about the performance.now function. That is basically it returns a timestamp of how much time has passed since the page was loaded. Actually, when I was implementing FPS monitoring, I've used this method to actually track how performant application is. Second thing is that is very handy are time and time end functions that are available in a console namespace. So what they do is that they allow you to track the difference in time between the time and time end was called, given that they share the same string literal. Since there are two functions that we need to call, in Rust programming language we can build a wrapper around it that would simplify the usage to just one line of code. And that is because Rust provides an ability to write destructors to the structures. And here you don't really need to understand what's going on. It's basically when we're creating a timer, when we're instantiating a timer, we are calling the time function. And when the destructor will be called, it will automatically call the time end. How would you want to use it? So again, getting back to the tick function that calculates next generation. Here we can see that we're instantiating time, and it's done within the code block of the tick function. The destructor drop will be called automatically when the execution will reach the end. When we will reach the end of the code block. So the example output of this would look like this. And yeah, from this demo you can see that, for example, one tick took, 18.576 milliseconds to computate. So this is very handy if we would like to track down the bottlenecks of our application and find how we can speed up those. And of course, DevTools Profiler, the thing that the most powerful and helpful, and that actually can be used for track almost all of the issues that you might encounter performance-wise. So let's get back to our demo. So you will not see it because of the frame rate, but if we actually set some crazy numbers, that here I'm setting the 60 frames per second, the cap, and I'm asking WebAssembly to calculate 20 generations per each frame. So now when I will click play, we'll immediately get to the end state of the game. But here in the top you see that the average frame rate was dropped down from 60 to 27 frames. And we can enable the profiler to track down why that happened. And here, if we take a look at the tick of one frame, we can see that it took 26 milliseconds for the whole computation. So probably we could get back to our code, check what's going on there, and try to fix the bottlenecks. And if we were to debug this application in real life, in real time, we would find out that the main problem is with live neighbor count. That is not very optimal performance-wise, though it's quite compact and understandable of what is going on here. The bottleneck is that we are using module operator for every cell of the universe, and that is quite performance heavy. Unfortunately, the optimized version, performance-wise again, that would speed up the code execution contains a lot of if statements and branches and all of that thing. Yeah, I'm not very happy with this.
You should use a monad. Yeah.
Sure. Don't mention. All right, so let's say we think that this was the problem that caused this slow frames per second. We've compiled again the application, and if we again get back, I will refresh it. Well, it's at least a bit better. Actually, when I was preparing it, there was 60 frames. But come on. There were like how many? 18 milliseconds? 26. And here is down to 4 milliseconds. So very
Awesome.
yeah. Back to the presentation. So last thing I will talk about what we have here is how we should approach building WAS modules for production. Well, you would most likely will be thinking that we should make the WAS module as small as possible. That will be because it will be small, it will be faster downloaded. Therefore, shorter time will be taken in order to start the application, and this will lead to the happy users. That's a bit different when we are speaking about WebAssembly, and we should take into consideration a couple of things. And the most important one is that the primary goal is to decrease the amount of time that it takes for the application to start reacting on, for example, user input. And so, since WebAssembly is already designed to be read by machines rather than humans, and because there is this streaming compilation, the whole process is already speed up to a very nice degree. But still, we can also compile the binary so it will be even better optimized performance-wise. Like, for example, let's say we have a for loop in which the compiler exactly knows that there will be like 4 iterations of some operations. So it will take away the for loop, and it will actually pass pass those 4 executions. So it will be a bit more performant in terms of computers. So let's take a look of what options WebAssembly, or better say Rust ecosystem, provides us out of the box. So cargo.toml file is something like package.json in JavaScript, where you specify all the dependencies, name, author, and there is also this section which is profile.release. Within it, we can specify how we want to compile the project for the production. First is debug equals to false here, which actually disables those debug symbols that I was speaking about. Link time optimizations, I will not describe what it's about, but it's basically a super cool, nice feature that will just simply speed up everything for you. And also there is this OPT level with two possible variants. One is S and another one is Z. Again, it's like default is S, that will basically the default settings for the compiler for the optimization. But if you really would like to shrink the size of the module, and that is your primary goal, you could use the second option that will do that, but it will also might be a little bit, it will take for the end module a little bit more time to be compiled and be ready for executions. In WebAssembly, there are different toolkits that would allow you to compile from your language to the WebAssembly. When I was speaking about AutoCAD, I mentioned Binarian. I mentioned mscripten. On the previous slide, I was talking about LLVM, and here is another toolkit which is called Binarian. And with this, it's a bit more advanced compared to the previous one. And with it, you can save extra from 15 to 20% while playing with those options that are listed here. But anyway, the key takeaway here is that you need to always measure, so that you don't spend like a lot of time trying to optimize the stuff that will bring you like, I know, 0.5 milliseconds of the difference, or don't just only think about the size of the WASM as a primary goal here, but always measure how it performs in real life examples. I would like to finish my presentation by saying a couple of things about the future. My conclusions are not different at all from the other speakers. I really believe that WebAssembly will shape and will really change tremendously the web industry in the future, in the next couple of years. We can already see that there are applications that are slowly porting their stuff to the web. And so this barrier between desktop applications and web applications will slowly become blurry until the moment we will probably not be able to differentiate one from another. And the coolest thing about it is that it will require no installation, and you will be able to reach your application by just typing a URL address in the browser. With that said, thank you for your time. Thanks for listening. Any questions?
If you want to communicate between JavaScript and WebAssembly, do you have any delay, or do you have to consider having how much time it will take between, if you want to communicate between JavaScript and WebAssembly?
Okay. So, honestly, I didn't really look really deeply into this topic, but there are issues from what I know when I was lastly checking. Actually, there was an article at hack.mozilla.org that explains how Firefox was able to speed up the communication between the two code parts. I haven't read that, so I will not be able to provide the deep answer, but there are concerns vendors are aware of that, and they are working on improving those things.